Dubai is preparing an industrial battery capable of releasing 1,400 megawatts of electricity for 6 continuous hours. That sounds like the final machine required to move solar energy into the night. But Dubai has also built a system that stores sunlight in thousands of tons of molten salt. Farther away in the Hata Mountains, it uses electricity to push millions of cubic meters of water uphill between 2 reservoirs. Why would a city need 3 enormous and completely different machines to store the exact same sunlight? Because even the giant planned battery cannot perform every job the grid requires. The Dubai Electricity and Water Authority recently tendered the 7th phase of the Mohammed bin Rashid Al Maktoum Solar Park. The announced design includes 2,000 megawatts of photovoltaic solar capacity. But the most significant engineering detail is what sits beside the panels. The plan includes a battery energy storage system rated at 1,400 megawatts with a 6-hour duration. That equals 8,400 megawatt-hours of total storage capacity. When a system reaches that physical scale, it looks like the ultimate answer to the sunset. A facility this large is designed to absorb massive amounts of solar power during the afternoon and release it smoothly into the evening peak. It offers fast electronic control and the ability to support precise grid balancing. Looking at the sheer volume of this planned electrochemical system, you might assume it makes all other storage technologies obsolete. If a city can simply order thousands of battery blocks and link them together, it seems unnecessary to engineer anything else. You just pour the concrete foundations, install the industrial enclosures, connect the heavy inverters, and wire them directly into the local substations. It appears to be the perfect modular solution for a rapidly growing desert metropolis. But the figure that makes this battery sound so powerful is exactly the same figure that reveals its strict operational deadline. To understand why one machine is not enough, we have to place all 3 of Dubai's storage systems through 4 strict engineering tests. We are not looking for corruption or failure. We are looking at this from the perspective of a system designer facing an almost impossible assignment. That designer must store solar energy in a form that responds quickly and lasts through the long night. It must survive for decades in the desert and operate at a massive urban scale. Test 1 measures speed. How quickly can the system detect a drop in solar generation and deliver replacement power? Test 2 measures duration. How long can the machine continue supplying electricity before it runs completely empty? Test 3 measures absolute scale. How much raw power and physical energy can the infrastructure physically handle during a massive demand spike? Test 4 measures survival. How long can the machine operate in extreme heat before it requires substantial replacement or a major mechanical overhaul? We are judging these technologies like competitors in a high-stakes industrial trial. If you were engineering a city grid, would you trust the fastest machine, or the longest-lasting machine, or the one capable of holding energy the longest? The reality of physics is that you cannot choose just one. When we run the speed test, the chemical battery wins almost immediately. Utility-scale lithium batteries are incredibly powerful for short-term grid flexibility. They work by converting electrical energy into stored chemical potential. When the grid demands power, the discharging phase simply reverses that chemical process. There is no massive mechanical steam cycle required to start up. There is no physical reservoir of water that has to build momentum before it can turn a heavy turbine. The electrical output can be controlled electronically in fractions of a single second. This makes chemistry the perfect tool for shifting energy across a few hours and balancing sudden fluctuations in supply. Because battery farms are built in modular blocks, they also offer extreme deployment flexibility. They can be installed relatively quickly on flat desert land without requiring a mountain or a custom thermal power plant. You can scale them up by simply adding more shipping containers full of lithium cells to the existing grid infrastructure. But this precise control comes with an absolute boundary. A battery can only return the electrical energy that has already been stored inside its cells. Its available contribution during an evening peak depends heavily on how full it is when the sun goes down. It depends on the ambient temperature and what other grid services it is actively performing. Chemistry wins the race for speed and control. Then the relentless clock begins to destroy its advantage. A 6-hour battery means the system is designed to discharge at its rated configuration over exactly 6 hours. It does not mean it independently supplies the entire city of Dubai for the night. To see the limit of chemistry, we can construct a hypothetical engineering stress test. Imagine a scenario where suspended dust slightly lowers afternoon photovoltaic generation. Because the panels produce less power, the battery enters the evening below its maximum charge. At the same time, cooling demand remains high because the nighttime temperature refuses to drop. Air conditioning units across the city draw heavy loads as their compressors struggle to reject heat into the warm night air. This forces the grid to draw more power just to maintain indoor thermal comfort. The grid operator cannot devote every stored megawatt-hour purely to bulk generation to meet this cooling load. Some battery capacity must remain strictly reserved for frequency control and split-second grid stability. The battery is not failing in this scenario. It is simply being asked to perform several demanding jobs simultaneously while the city continues to draw massive amounts of power. At hour 6, the electrochemical system does not slowly become less useful. It reaches a hard mathematical deadline. When the chemical potential is exhausted, the system simply stops producing electricity. Dubai already knew this physical limit and had already built a longer duration answer. But this second machine does not store electricity directly. It is a battery that contains absolutely no cells. The fourth phase of the Mohammed bin Rashid Al Maktoum Solar Park was inaugurated in 2023. It delivers 950 megawatts of combined capacity. While part of that generation comes from photovoltaic panels and parabolic troughs, the visual centerpiece is the 100-megawatt solar tower. It looks like a clean, futuristic monument standing in the sand, but this machine operates on a completely different principle than a chemical battery. It does not store electricity directly. Before its final stage, it contains no electricity at all. It stores sunlight as extreme heat. Around 70,000 precision tracking mirrors called heliostats surround the structure. They follow the sun across the sky and concentrate its radiation onto a central receiver sitting near the top of a 263-meter tower. Inside that glowing receiver, more than 1,000 thin tubes carry a specially formulated molten salt. The salt absorbs the concentrated thermal energy and flows downward into massive insulated storage tanks. This thermal storage system holds 5,907 megawatt-hours of energy. It can keep that heat trapped inside the hot tanks for hours after darkness falls over the city. When the grid finally demands power, the hot salt is pumped through a heat exchanger. It boils water to produce high-pressure steam. That steam spins a conventional turbine, which drives a generator to push electricity back onto the grid. It is a brilliant way to capture the sun and delay its release. Salt can wait much longer than a lithium system, but it can only do so by building an entire thermal power station around the captured sunlight. Every engineering advantage creates another layer of machinery. To extend solar energy deeper into the night, the concentrated solar power system relies on a massive chain of physical components. To capture the light, Dubai needs tens of thousands of precision mirrors and automated tracking mechanisms. To catch the heat, it needs a heavy thermal receiver installed at extreme elevation. To move the heat, it requires heavy-duty pumps and heavily insulated pipes to prevent thermal loss. To store the energy, it needs massive hot and cold salt tanks. To recover the energy, it requires complex heat exchangers. To turn that heat into electricity, it needs massive volumes of water to create high-pressure steam. To use that steam, it requires high-speed turbines and heavy electrical generators. This is the true cost of longer duration. The tower looks like a sleek obelisk from a distance. Behind that clean image is a thermal power plant of enormous mechanical complexity. Every moving part requires rigorous temperature management and highly trained maintenance crews. Operators must strictly prevent operational problems within the molten salt cycle. If the salt cools too much, it can freeze inside the pipes and cause severe blockages that are incredibly difficult to clear. If a single heavy pump fails, the thermal transfer stops completely. The point is not that concentrated solar power is defective or poorly designed. The point is that long-duration storage is not achieved by one elegant solid-state object. It requires a sprawling industrial machine that demands continuous operational oversight and heavy maintenance budgets. Salt extends the clock and solves the duration limit of chemistry. But Dubai still wanted a machine capable of surviving for generations. To find it, we have to leave the desert and cut into the Hatta Mountains. In 2025, trial operations began for the Hatta Pumped Storage Hydroelectric Plant. This facility relies on the most physical form of storage in the entire story. It stores energy using gravity. The project features an upper reservoir holding approximately 5.3 million cubic meters of water. It connects to a lower reservoir through a 1.2-kilometer underground water tunnel. When solar electricity is abundant on the grid, reversible turbines use that power to pump water from the lower lake to the upper basin. Electricity becomes gravitational potential energy. When the grid faces a sudden demand spike, the system opens massive valves. The water accelerates downward through the tunnel and spins the turbines in reverse. Mechanical energy becomes electricity again and reaches the grid within approximately 90 seconds. The Hatta plant provides 250 megawatts of generation capacity and 1,500 megawatt-hours of storage capacity. It achieves a round-trip efficiency of 78.9%, but its greatest engineering advantage is endurance. Unlike electrochemical batteries that chemically degrade with every single cycle, this civil engineering structure has a planned operational life of up to 80 years. It relies on mature physical principles that have been tested around the world for decades. There is no requirement to replace thousands of electrochemical cells on a strict maintenance schedule. However, this monumental scale introduces a severe limitation. You can order thousands of lithium batteries and place them almost anywhere near a substation. You cannot order another mountain. Pumped storage is strictly controlled by geography. It requires a massive elevation difference and highly specific geology capable of holding the heavy reservoirs. It demands huge physical space and long construction periods involving major civil works. Water solves the problem of aging, but geography strictly controls where it can exist. We have placed 3 enormous machines through the engineering tests. If you look at the raw specifications, you might try to declare a universal winner. The lithium battery field is the undisputed champion of rapid electronic response and deployment flexibility. The Molten salt tower wins on thermal duration and extending heavy generation deep into the night. The mountain water system wins on physical survival and generational asset life. To understand how they compare, you only need to know the difference between megawatts and megawatt hours. Megawatts describe the rate at which power can be delivered to the grid. Think of it as the physical width of a pipe. Megawatt hours describe the absolute quantity of energy available over a specific period of time. Think of it as the total size of the reservoir feeding that pipe. The battery provides a massive pipe, but a strict time limit before the reservoir runs dry. The salt provides a steady pipe with a much longer duration. The mountain provides a fast pipe built to last for nearly a century of continuous operation. The mistake is assuming Dubai built these 3 systems to actively compete against each other. There is no universal winner because there is no perfect storage technology. Every single victory creates a structural weakness that another machine must cover. Chemistry is incredibly fast, but it degrades over time and reaches a hard mathematical limit. Salt is long-lasting but mechanically complex and constantly vulnerable to thermal blockages. Water is incredibly durable but geographically trapped in the Rocky Mountains. None of these machines can run the entire city alone. 3 storage systems are completely useless if they release their energy at the wrong moment. A battery discharging too early leaves the grid completely exposed during the actual midnight peak when air conditioning loads are highest. Water flowing down the mountain at the wrong hour wastes valuable gravitational potential that cannot be recovered until the next sunrise. The 4th machine is not a physical battery you can photograph in the desert. It is the vast electricity grid itself. It includes advanced forecasting systems, high-voltage substations, millions of data sensors, and heavily constrained transmission capacity. It relies on precise dispatch software, control room operators, and critical reserve management. To understand the immense complexity, look at the rapid decision sequence happening every single afternoon. Should incoming solar energy charge the lithium batteries, or should it pump water uphill to the upper reservoir? Should the concentrated solar power output be used immediately or heavily preserved for later in the night? Should HATA generate power right now or remain safely available as an emergency spinning reserve? What happens when the solar forecast changes suddenly due to incoming cloud cover or suspended dust? What happens when a critical transmission corridor becomes thermally constrained by the extreme desert heat? The visible monuments in this story are the sprawling battery field, the glowing solar tower, and the massive mountain reservoir. But the system that actually makes them useful is far less photogenic. It exists inside quiet control rooms filled with heavy switching equipment and glowing data screens. It depends on highly accurate weather forecasting, heavy grid infrastructure, and relentless human judgment. To see how this hidden machine coordinates the other three, we have to place all four into one hypothetical operating test. Let us create a hypothetical engineering stress test. This is not a prediction that Dubai will experience a sudden blackout. Imagine a scenario where several manageable problems occur together on the exact same evening. Suspended dust suddenly lowers the afternoon photovoltaic generation across the massive solar park. Because of this drop, the giant lithium battery field enters the evening peak, well below its maximum charge. At the exact same time, urban cooling demand remains incredibly high across the metropolis. Simultaneously, a specific section of the thermal molten salt system is undergoing scheduled mechanical maintenance. The HATA mountain reservoir must firmly retain some of its water as an absolute emergency reserve for the broader network. And finally, one major grid transmission connection is currently constrained by heavy thermal loads. No individual problem on this list should be portrayed as a catastrophic failure. The extreme tension comes entirely from the coincidence and the sheer scale of required coordination. This is the exact moment the invisible fourth machine takes over to balance the portfolio. The remaining lithium batteries immediately respond to rapid fractional changes in grid frequency. The active molten salt system provides a heavy baseline of dispatchable thermal energy over a much longer period. The HATA mountain facility supplies rapid mechanical power and critical reserve support to stabilize the heavy grid load. Human grid operators quickly redirect electrical flows around the constrained transmission corridor. Automated forecasting systems constantly update the precise dispatch plan minute by minute, and the wider conventional generation portfolio continues supporting the entire city in the background. None of these individual machines saves Dubai alone. The massive power system only works because no single machine is ever expected to save it alone. These three enormous storage projects do not simply eliminate operational risk. They carefully divide that risk into different timescales and assign each specific problem to the machine best suited to handle it. Dubai stores its captured solar energy in three distinct physical forms. It relies on chemical potential, thermal energy, and gravitational potential. The reality of physics means that every single conversion loses some valuable energy along the way. Every individual machine requires massive capital investment and heavy dedicated infrastructure. Each system demands relentless maintenance schedules, complex control systems, skilled human operators, and a robust wider grid. Dubai did not miraculously find one perfect storage device that solves every single problem. Instead, it engineered a highly complex portfolio of imperfect machines. Within this carefully balanced portfolio, chemistry successfully supplies the speed. Heat securely supplies the duration, gravity reliably supplies the endurance, and the invisible electricity grid supplies the vital coordination. Dubai is building a clean energy future, but it will never be protected by just one perfect battery. It will entirely depend on a massive chemical machine that reacts almost instantly to frequency drops. It will rely on an immense thermal machine that securely holds the heat of the sun long after darkness falls. And it will always need a monumental mountain machine built out of solid rock to survive for generations. The real engineering achievement is not simply capturing and storing the sun. It is knowing exactly which imperfect machine should release it and when. This documentary uses publicly available technical and project information for educational analysis. The battery project in Phase 7 is an announced and tendered design rather than an operational facility. The concentrated solar power project is fully operational. The Hada hydroelectric plant successfully entered trial operation and began exporting electricity. The stress test described is strictly illustrative and is not an outage prediction. Actual system performance can vary significantly depending on operating conditions and grid dispatch strategy. Which system would you trust most to support a massive city? Lithium batteries, molten salt, or mountain water? Tell me your engineering choice in the comments below. If you want to understand the complex systems that keep the modern world running, subscribe to the channel.